Okay, so if we have our higher level language program, we need to know how things are translated in order to start my program in the memory. We went to earlier we went earlier and covered these things like in a glance, but now we need a little bit to go a little bit deeper to understand each step and what's exactly happening there. So first, when you have the high level language, you will have a compiler, and inside that compiler, it will transfer whatever the language that you have entered, and then to an assembly language program. After you have an assembly language program, then you will have your assembler that actually will begin to create the machine language. But with the creation of the machine language, you also have some library routines or some library inside that machine language, which you can actually use it with your machine language module and link both together using a linker. And after you have the linker, you will get basically a working or an executable machine language program. And after having a machine language program, you can just like load it basically to your memory. When we mentioned loading here, that's basically you are initiating everything, initiating like the arguments, stack pointer, frame pointer, global pointer, all the variables and stuff like that. All of this is just like is loaded in the memory. So the assembler or compiler will translate the program, the machine of all of these pieces to build basically a complete program. So header, text segment, static data segment, relocation information, and so on and so forth. I'm not expecting that you remember all of these things by heart, but just like conceptually understand what is happening behind the scene. Because I may give you like a certain particular task and ask you like where this would happen. Would this happen in that, between the compiler, this like the task of the compiler or the assembler or stuff like that. So you need to get a sense of what is really happening in that regard. So when we do the linking of the object modules, of course, we'll do a merging of segments, and then we'll determine the addresses to resolve the labels. And also, we will define external references and basically patch location. At the very end, when we are doing a loading of a program, as I mentioned, would expect that you will set up the arguments on the task, initialize all of the registers that you may have, jump to a startup routine. Also, you might also create a virtual address space and then read the header to determine the segment size. I'm not expecting that you will remember everything this as a list, but just do understand what would we expect in basically loading program. Also, while we are doing the linking, there is something called dynamic linking. And in that, one of the options that actually to link and load library procedure only when it is called. So if you have your program, so instead of linking or loading all of the library to your code, this will be not efficient, computationally not efficient. Just link whatever is called inside your program. So if you don't need it, you don't have actually to link. And that would create like a much higher efficient, basically, program in that regard. So what we have covered so far is a MIPS, as we mentioned, simulation, but also there is something called ARM, one of the most popular embedded cores. As you can see from here, the ARM and the MIPS approximately have most of the things the same, except the data addressing mode and the register. So in our case, it is 32 by 32, but in the register, the ARM, it is basically 15 multiplied by 32. Also in the MIPS, if you recall, when I write any of the instructions, we have, for instance, register or R format. In this R format, as we have explained earlier, that we have the opcode for 6 bits, RS, RT, RD, and then shift amount, and then function. But also, as you can see from here with the ARM processor, also I have RS, RT, RD, and then I have also the operand, and then another things that corresponding to something like a function or so. So it's not exactly the same, because actually both of these companies not the same, and they are not using the same exact assembly code, but conceptually they will build their instruction or the types of their instructions with the same concept, that what we need to do this, what we need to do that, and stuff like that. If you look at the data transfer, like as an example, I format using load word or store word. As we have covered earlier here, the opcode RS, RD, and then constant, but with the ARM processor, again, RS, RD constants, opcode, but also we have something else here. With the branch, MIPS is exactly the same as the I format, but with ARM processor is a little bit different. With the jump, as we mentioned earlier for the MIPS, opcode, and then the whole constant for address. With the ARM processor, again, something very similar to that. So we are introducing this not to ask you like remember everything about the ARM processor, but just to show you that if you actually learn one of the assembly language, it will be very easy to understand another language, another assembly language, because conceptually they will be very similar as a concept. What registers we will need, how to actually implement that, and so on and so forth. Another processor is called Intel, and we began with the 86 series. So let's try like to go over the evolution basically of the Intel processor. So in 1974, they had like the 8080, and interestingly, they had only an 8-bit microprocessor. In 78, it has been extended to 16-bit, and they call it 8086. And then they have the 8087 in 1980, and they have been able to implement actually a floating point coprocessor. Then in 1982, they had the 8286, and it was like jump to two 24-bit addresses. In 1985, they had the 386, but again, a jump to 32 bits. And in 1989, they have the 486, and it was very famous at the time. They have the pipeline. And then superscalar, it has been expanded 64-bit data path with the Pentium in 1993. And then Pentium Pro in 95, Pentium 2 in 97. Then in 1999, we have actually the Pentium 3, and then Pentium 4 in 2001, and so on and so forth. You can just like go over these kind of things by yourself. Again, this is just for your information. We are not expecting that you would remember these kind of things. Also for x86 register, we have also some registers basically that are needed in this x86, as we have in the MIPS 32 different. Do you remember like when we had also T0, T1, and S, and all of these things? We have also different things here with the x86, which has like different tasks and so on and so forth. You can see here also code segment pointer, stack segment pointer, data segment pointer, and so on and so forth. Again, we are not expecting that you remember that, but these just give you an indication that at the very end, similar concepts. Yes, they might not be exact same registers, yes, but again, I am having a register. I need to copy something to the memory and go back and forth and stuff like that. And then I might have my instruction a little bit differently, as you can see from here. So doing by push, pop, and stuff like that. You can have also jump, unconditional jump. You can call a function or a routine. You can do a loop. You can do a move. Push and pop is something like, in our case, going to the stack, yes, and getting back from the stack and stuff like that. Add, subtract, it is the same. Shift left, shift right, or XOR. Some of these kind of like very similar to whatever we have in MIPS, but not all of them. We are not expecting that you have to remember these, but this does not mean that I'm I can't get like or to write any instruction with any other language and explain to you like what is that exactly is doing, and then ask you to implement that in MIPS. This can happen. So I give you any instruction and explain what is the purpose of that instruction, and then ask you, please implement that using the MIPS. This could happen, but I'm not expecting that you will memorize any of these kind of operations. So here we just finished chapter 2. We are moving to another important chapter called arithmetic for computers. So arithmetic of computers basically will do some operations like addition, subtraction, multiplication, division, and we'll see like how we will deal with the overflow. Also, we'll explain floating point, real numbers, and stuff like that. So assume that we would like just to do this simple operation, 7 plus 6. We will write 7 here in binary, which is 1, 1, 1, and all zeros. And then we will write 6 in binary, which is 0, 1, 1, and then all zeros. And then we'll do the addition. 1 plus 0 is equal to 1. 1 plus 1 is equal to 2. 2 means I write 0 and then carry 1. 1 plus 1 plus 1 is 3. 3 is written as 1, 1, and that's why I have here 1 and the carry 1. 1 plus 0 is 1, and then zeros, zeros, and so on and so forth. We need, of course, to be aware that when we would receive an overflow and when not, or how I would interpret that this is an overflow or not. So of course, if I'm adding positive and negative operands, there is no overflow. Why? Because if I'm adding positive and negatives, if I have been able to write that positive number in 32 bits, and then I would subtract another number that is also written in 32 bits, that number would be less than that positive one. So if that positive number was basically it was written in a 32 bits, so of course after I subtract a number, it would be of course sufficient also in 32 bits. And that's why if I have a positive number basically added with a negative number, the results no overflow. But what will happen if I'm adding 2 positive operands or I'm adding 2 negative operands? If I'm adding 2 positive, so if this is positive and this is positive, and I'm adding these together, I might have an overflow. Because if I had here, as an example, a number 5 and 6, the results 11, I might have that 11 written in a higher number of bits than what was written, what was used in 5 and 6. So if I'm adding 2 positive, there might be a chance to have an overflow. But how I would know? If I'm adding 2 positive numbers, I would expect the number output to be positive as well. So that means that the sign bit should be 0. So if I found the sign bit is equal to 1, of course, I would understand that there is something wrong and there is an overflow occurred. And that's why, if this is the case, I would expect an overflow. Similarly, if I'm adding 2 negative operands, if this is negative and this is negative, I'm adding them. If this was negative 5 and this is negative 6, negative 11, again, I would expect that negative 11, for whatever reason, might need, or that results might need a higher number of bits. I would expect that if I'm doing an addition of 2 negative numbers, that the result will be a negative number that's higher than both, but it's still a negative number. So if it is a negative number, I would expect that the sign bit should be 1. But if I will find the sign bit is equal to 0, again, an overflow. Let's see like the integer subtraction. Assuming that I have 7, I have the 6, I would like to do the subtraction. So it's 7 plus minus 6. So this will be 7, and then this will do the plus minus 6. Minus 6, you can write this easily in 2's complement. When you write this easily in 2's complement, so it will be 7 minus 6, and at the very end, as you can see, the result is 1. Again, if I'm subtracting 2 positive or 2 negative, no overflow. Because if I have a positive number and another positive number and I'm doing the subtraction, the results will be less than any of them. Or the biggest, it will be equal to one of them if one of the operands is basically 0, correct? So no overflow. The same happen if they are both negative, and then this is the negative, so negative negative means negative plus. Again, the results, there is no overflow. When I would expect an overflow, if I subtracting positive from a negative, meaning let's say I have -5 and I have another positive number called 6, and I am subtracting both of them. -5 minus 6, again -11, this is bigger than both of them, so I would expect that there might be an overflow. I know in advance that the results has to be a negative number, so if it is a negative number, that means that the sign bit has to be 1. So if the sign bit is equal to 0, again that's an overflow. How about the opposite case, subtracting negative from a positive? So I have here the positive, and I have here -5, and then subtraction. 6 negative -5 is equal to 11. Again, that number is higher than the most positive number, so it might result in an overflow. But I know that the results here has to be positive, and if it is positive, the sign bit would be 0, and that's why if I have a sign bit of 1, again, that means that I have an overflow. And in that regards, of course, if there is overflow, then I have to take care of all of these kind of things.